Thank you so much for joining me today. My name is Aloysious Tasch, or Alo for short, and I'm an incoming freshman at the University of Texas at Austin. So in YSP, I'm a research associate in the Artificial Nuclear Life Project under the mentorship of Dr. Pedro Maldonado and Dr. Clement Vidal, as well as my fellow RA David. And together we've been exploring how to study and model stars using reaction networks. So a little confusing. I'll get more into that later. But to conduct our research, we used a couple of different tools. So some of these are more well known, like Python, for example. But the second is like the key framework of our project. It's called Chemical Organization Theory, abbreviated as COT. So before we dive into more about what our project is about and what we did, I'd like to give a brief introduction on COT because it's just so essential. So it was like our fundamental framework, and it's just the fundamental framework in general for modeling reaction networks. And a reaction network, by the way, is where species convert into one another using or through reactions. So think of a bunch of different points on a map. Each of those is a species, and the lines between them are the reactions. That's kind of how I see it. There's a subset of reaction networks called organizations, and these have requirements. The first is that they must be closed, meaning no new species are introduced into the set, and second, they are self-maintaining, meaning that every species consumed is regenerated by other reactions in some way. So they're just self-contained, no really outside influence. This leads us to the concept of autopoiesis, which describes systems that are continuously produce and maintain their own components. So human bodies, for example, and really any living thing, these are all examples of autopoietic systems because they're all autonomous and they make and remake their own parts for the most part. So what exactly, or how exactly does this connect to our project, which is titled Artificial Nuclear Life? I was a bit confused at first, for example. So we can model a star's nuclear reaction network using COT, which essentially turns these big, terrible balls of hot gas into simple or more simple algebraic equations. And we can also make fun maps out of them. The fun part, actually, well, at least in my opinion, is the life part. We can explore whether stellar systems exhibit properties analogous to autopoietic systems, and whether these properties could help us think about what we actually consider life to be. A few scientists have done deep dives on this abstract subject, and one of these is actually the Stellivore hypothesis, which was proposed originally by Dr. Vidal, one of my mentors. And it proposes that certain interacting binaries may actually be manifestations of advanced extraterrestrial civilizations that get their energy by feeding off of other stars. And this is explored more in depth by another YSP project, which is presented at 5 p.m. today. So make sure to go check out their work because they will explain it more in depth. So for our actual kind of like projects, we focused on applying whether systems could exhibit properties analogous to autopoietic systems. So basically applying characteristics of living things to non-living things, stars. So even though we didn't discover an alternative form of life, we did have a lot of fun using chemical organization theory, and also learning coding and even astrophysics as well, because it's stars. So our actual learning was done through homework assignments, and these were specifically called tasks. And we used Jupyter Notebook and Python to conduct these. Before I get into this, just some brief context. As I'm sure most of you know, stars change over time. They have life cycles. And as they progress through these life cycles, the core eventually contracts, and the temperature T and density rho increase. These new conditions make new reactions possible because changing conditions, new pathways open up. And these generate new nuclear species, which is great because now we have more stuff and can do more things with this. So this homework specifically investigated what nuclear species would be produced, starting from just a single proton as we moved through different stages of the stellar life cycle. To find answers, we used a concept called operational closure. It essentially asks, starting with a limited set of species, what additional species can be generated through the reactions that are accessible within this set. So in this case, we started with only hydrogen. So not really a lot to work with. However, over time, you'll see just how much and just how complex the system eventually becomes. So the first task was to implement the mathematical function that describes the rate of a nuclear reaction as a function of temperature. because if you remember, temperature changes as the star ages. We used a 7-parameter parameterization using reaction rates from the NACRE and GINA ReaClib databases, which are lots, just basically they collect reaction rates for all these different nuclear reactions. There's like thousands of them. Oh, I'm sorry. T9 represents our temperature divided by 1 billion Kelvin, and the reaction rate is calculated using an exponential function with 7 coefficients, 7 parameters. So after implementing the function into our code, we plotted the reaction rates for several reactions across temperatures from 0.005 to 1. And remember, it's divided by 1 billion. And the dotted line here marks the approximate temperature of the center of our sun. Yeah, so kind of crazy. The resulting graph that was generated by the code shows all the different nuclear reactions and when they dominate based on the temperature. And there are two main hydrogen burning pathways to look out for. The first is the proton-proton chain, and the second is the CNO or carbon-nitrogen-oxygen cycle. At relatively low temperatures, the proton-proton chain dominates completely. But as the temperature increases, reactions involved in the CNO cycle become more favorable. And the CNO cycle becomes the primary form of hydrogen burning. Task 2. So in task 1, we identified all the reactions with non-zero rates at different temperatures. But just because a reaction technically qualifies doesn't mean it's actually going to happen because there's other variables. So we need a more precise criterion for determining whether a reaction happens quickly enough to matter. The speed of a reaction is another big factor. This assignment specifically calculated the reaction's production flux using different factors. So how much was produced, and then compared it to a predetermined threshold. Reactions were then either sorted into active, meaning they're fast enough to have a meaningful effect, or inactive, where they still technically happen, but they're just so slow that they're insignificant. We don't really care about them. There's also another thing we need to take into account. A reaction can't happen if its reactants don't exist yet. And we hadn't really considered that before. We'd been doing calculations in isolated environments. We hadn't been taking into account the previous, I guess, context. So remember that we started with only hydrogen. So clearly, this limitation is quite important. We factor this in for each of the 5 stellar stages in the assignment, which are hydrogen burning at PP chain onset temperature, hydrogen burning at the CNO onset temperature, helium burning, carbon burning, and advanced burning. These 5 over here. And this is the table showing all of the reactions and when they happen at each stage. So yeah, you can see how it changes over time. So yes, this was task 2, and there's task 3, which is up next. Task 3 is where we actually applied chemical organization theory to our nuclear network. So we took the active reactions identified in task 2, and we used them to calculate operational closure, which, if you recall, is asks what additional species we can create based on the original set. And we applied this to our system. And remember, we started with only one species, which was hydrogen. So we're trying to see how much we can produce from this original, I guess, set of species. So starting with the proton, we look for active reactions first. We allow those reactions to produce products, and then we add those new species to our set. And we repeat this until we get all the species possible. We did this over 5 stellar burning stages and generated a table of the active reactions and species over the stages. And this is, yeah, the produced thing table. And the stages is 0, 1, 2, 3, and 4. And we also plotted the number of species per stellar stage, and this stayed at relatively constant 10. There's some changes, but it's the number itself stays constant. So yes, this was like the actual applications of everything we had learned about chemical organization theory to our previous reactions that we gathered were hypothetically possible. And then task 4 was kind of just a summary. It was about interpreting our results. So one interesting thing we explored was how a reaction can become kinetically accessible without becoming structurally accessible. So what this means is that, for example, the CNO cycle may become extremely fast at high temperatures, but for it to occur, we need carbon, nitrogen, and oxygen. as starting points. And if we don't have those, even if the reaction is hypothetically possible, it's not going to happen because it doesn't have everything it needs. So basically, there are multiple factors, and temperature alone doesn't determine which reactions happen when. There's a bunch of different variables, a few of which I mentioned. So additionally, we found that if we start with a single proton, we just can't reach every species involved in the CNO cycle, because it requires an initial seed of heavier nuclei. So basically, the CNO cycle isn't completely possible starting from just one proton. So this is especially relevant to population 3 stars, which initially lacked the carbon, nitrogen, and oxygen needed for the CNO cycle to actually occur. So these heavier elements, in order for the CNO cycle to occur, must be produced and accessed through alternative nuclear pathways. Um, so yeah, that was pretty interesting. And that was our presentation. So thank you so much for your time. It was so much fun, but it was a little bit difficult to compress everything we learned into a short presentation just because we learned so much and had so much fun. So I hope it wasn't too intense or fast-paced. I'd like to thank my wonderful and supportive mentors, Dr. Clement Vidal and Dr. Pedro Maldonado, as well as my very supportive teammate, David, who helped me through the process of code. I'd also like to thank Dr. Lau and everyone else who made this amazing program possible. So thank you so much for listening. I really appreciate it.